Thank you. Hopefully, is the microphone on? Yeah. Well, it's a deep honor today, and I feel like I should actually just stop right now and we can all start drinking. I'll do my best to really provide you with some excitement, but I really want to thank everybody for coming today. My family all came from far away, and they're all here, and they know who they are. Thank you for coming. And most importantly, I have to thank my wife, Ellen, for everything wonderful she does that makes everything possible. And what I want to do at the beginning, though everybody's kind of told the story, so actually most of my personal anecdote thunder has been stolen, except I still have one surprise. So when I came to the Institute, the place has an odd tradition, which is that you wear a hat. All of you who've been here as visitors know that when you arrive at the Institute, you get a hat. And it was the first place I'd ever come to where you have a hat. I thought that was kind of unusual. So I'm looking through my hats here. Here we go. And so when I came, and Deborah's here somewhere. There's Deborah. She probably started this tradition. You also have an acronym, right? So we have the acronym ITP. And so, of course, here I have what's now a collector's item, an original ITP.UCSB cap, right? Which is what you got when you arrived. Again, you can only find this on eBay. Price has gone way up. And we wore this hat for many years while we were doing a lot of work here at the Institute. As David talked about the building. I'll put that there if it holds up. We'll see, because I have a few hats. And that was, David already mentioned, we spent a lot of time working on the new wing. That was, of course, all triggered by the donation we received from Fred Kavli. And, of course, when Kavli came, then we had to add the K. So here you go. So now we have KITP. So again, you get an acronym and then a cap, right? That's the tradition. Okay, so here's the KITP hat that we now all have. And of course, these are not collector's items. You can still get them for I think they're $8. Less than your parking today. Less than parking, I think. Is that right, family? Yeah. It's about the same. Okay, good. Now, for me, the deep honor today is to be honored by Wayne, Simon, Diana, friends, acquaintances. They've all told the stories of how we met. Wayne told the originating story of being in my office. Wayne and I met I first heard about the observatory when I was at a meeting in Amsterdam. It was announced at the meeting by Virginia Trimble, who's a professor at UC Irvine, long friend of Wayne, announced at the meeting that there was going to be a new observatory established that was going to build 1 or 2 meter telescopes so that you would be able to observe things all the time, and the observatory was based in Santa Barbara. Well, as somebody who lives here, I was sort of surprised that I hadn't heard this. And she said to me, "You'll find out soon enough." And indeed, within a month, Wayne and I met, and you heard the story, and that's been a very exciting ride. And today and yesterday, Wayne and I were working with the Scientific Advisory Board for the observatory, who come here from all around the world to give scientific advice to the observatory. So we're well on our way, and I think everybody should start to see science coming out that's unique from the observatory within probably 3 years, is I think where we're at. And that started this relationship with Wayne, and thank you, Wayne, so much for the recognition today. Very deep for me, so thank you. Okay, hats. So I forgot one. Sorry, Wayne. Right, hats. LCOGT has a hat. Right? Sorry, I forgot the props. Wayne, I don't need to give you this. Maybe Simon should have the hat. Yeah, okay. Okay, so that's the way. I'll put it here for now, so the continued props. Okay, so that's the LCOGT hat. Well, starting in 2007. It's already been mentioned, I got very engaged in the Engineering Academy. That happened because my daughter came home and said, Lars, Amir, my teacher, demands you to be there this evening to make an announcement. That was 3 years ago. A number of us showed up. Thankfully, we formed a foundation. The board of directors of the foundation's in the room. We've all been working very hard on that. So that, of course, gives you that, a logo, and then a hat. Thankfully, I didn't have a hat. I was sad to say. I don't know how that happened. But thankfully, one of our board members had a hat. Now, this hat, you could tell, has been worn in competition. I'm thinking, right, Sandy? Yes, okay. And though I met Simon first at the KITP Directors Council, the engagement we've had most recently is in the context of the Engineering Academy. And both Simon and Diana really did see what we were doing there and have been big supporters and personal advisors to those of us who are really trying to pursue a very simple goal, right? Simply stated, we just want to transform education. And we're going to start in California, and I'll declare victory if we achieve that. So then, of course, I can't help. So those are my logos. That's it. Okay. You've already heard that I have many engagements. But of course, I can't stop without thanking David Gross and the Institute for basically enabling the permanent members to really pursue our passions, both in science and all these other things. These are distractions as viewed by others, but for me, this is really what I enjoy doing, both the science and the other. And so I think to be at a place where that's enabled, both from the university perspective and the Institute, is a real strong point about UCSB, and I think it's what makes this place actually quite special. Okay, so now you're all asleep. You all want to stop, but I'm going to give you 40 minutes of science whether you want it or not. Okay, so first thing, you all need to learn how to count. So in school, you were taught 1 Mississippi, 2 Mississippi, 3 Mississippi. Well, we have 1 supernovae per second in the universe. So get ready. Here we go. 1 supernova, 2 supernova. This is to wake you up. 3 supernovae. Okay, that's the frequency of these events in the universe. And I'm studying those with a very fantastic group of people, some of whom are in the room. These are the collaborators I've been doing work with most recently. Dan Kaysen, who is now a young professor at Berkeley. Kevin Moore, who's here in the audience, is a graduate student. Heisen Ellemans, who's at University of Nijmegen. Bill Paxton is here, one of our rare senior fellows, and here at UCSB, Wayne is a senior fellow. That title didn't exist in the academic manual until I wrote it. And Gus Gurley, I believe, right? So you can all thank me for the fact that there's now 1 page in the red binder. Evan Scanapico is a postdoc here at KITP, is now on the faculty. Ken Shen, who just finished his PhD, is now at Berkeley. Justin Steinfeld, I think, is in the room somewhere. He's a graduate student working with me. And Nevin Weinberg, who was a postdoc here and is about to join the faculty at MIT, which is an institution I send money to every year. Okay. So what I want to tell you today is how stars explode, why it happens, and how we observe them. And the main thing we've done for many years is to understand the source of energy that causes the explosion. And roughly speaking, there's 2 sources of energy that can cause that. Gravity, the fact that as an object contracts upon itself, it's getting deeper in its potential well, and that releases energy. And nuclear energy, the fact that what's made in the Big Bang is predominantly hydrogen and helium. However, as you fuse those elements up to the most stable isotopes, roughly around iron, that releases energy. And if you can find a way to get your hands on that energy source, you can do something with it. Stars that we see on the sky, that you see on the sky, basically tap into these 2 different energy sources. But they do it at a rate that's very slow, in the sense that they only do it at the rate they need to live. Now, you can ask if there's an analogy there. Some people might be consuming more energy than they need. As we'll discuss, that's a supernovae. If you're behaving well and consuming only what you need, you're a star. Okay, so keep that in mind. Okay, so supernovae do the opposite, as I'm going to explain. They release this energy so fast, so suddenly, that the object has no choice but to basically disintegrate into space, and that's what I want to talk about today. So I'm going to sort of leap in and tell you things. The first part of this talk is basically telling you things that anybody could have told you 25 years ago. The second half of the talk is going to be to tell you things that nobody could have told you 3 years ago. Discoveries we've made, by we I mean the astronomical community, predictions that we've made personally, theoretically, and post-predictions we've made theoretically after the fact, right? I want to be ahead of the observers, but it's really, really hard to do that because they keep building more telescopes. Okay, so at the end of a star's life, as I said, a normal star gets to burn its hydrogen to helium, its helium to carbon and oxygen, continues up. At the end, it's made a ball of iron, which is the most stable isotope that's at the center of the star. This is a star that's roughly 15 times the mass of the sun at the beginning. At the end of its life in this case being maybe only 10 million years. I say only 10 million years because the universe is 10 billion years old. So 10 million years is very short. It has a ball of iron with roughly the mass of the sun. And then it has elements of decreasing atomic weight, silicon, oxygen, carbon, helium, going out to the surface, which is still the original material, that because it's been at the surface of the star has never gotten hot or dense enough to actually undergo fusion. But what happens is eventually, at the center of the star, there's no longer any way to get energy, nuclear energy, out of this iron. Iron is the most stable isotope. If I take two iron nuclei together and fuse them, that actually costs energy. It's not going to release energy. And so there is no source eventually in these stars of energy other than gravity. So this object then says, fine, I will just collapse. And that's what happens. This iron ball, which is roughly the radius of the Earth, but the mass of the sun, so its density is about 10 million times that of water. And it's very hot. That's Kelvin. Doesn't matter. You can put it in Celsius if you want. Doesn't change the digit. This thing collapses suddenly upon itself. It gets to such high densities that the iron nuclei themselves are touching. At that point, it can't collapse any further. It becomes, if you will, an incompressible ball. The rest of the material falling on it bounces off that ball and goes out, ejecting all of this matter outwards. And what's left behind is either what we call a neutron star or a black hole. Now, you find these in supernova surveys, and I'm going to explain to you how we get the brightness. The way the observers find them, of course, is they look for the arrow on the image. Okay, so here's the arrow. There's the supernovae. Okay, in a prior image, that wasn't there, and so you know something happened. And this is how they look. This is a spiral galaxy. Well, I don't have to tell you that. But these are young stars being formed, and so other galaxies have just mostly old stars and don't look nearly as exciting. Those are called elliptical galaxies. Doesn't really matter for this talk. So this is how these objects appear. Now, NASA, of course, after spending billions of dollars on satellites, makes discoveries and then spends about $50 to make a movie. So I'm going to show you the $50 movie from NASA of a supernovae going off. Of course, there's no soundtrack. So if the audience wants to provide a soundtrack, they can. I'm not sure if I should encourage that. I don't know, Kate, you want to do a soundtrack? And I'll explain then what happens. So get ready. There it goes. That's what it. And what they're trying to recreate with the artist's view is the remnant that's made of all the material that's sent out. And I'm going to talk about how we understand the brightness of these events. They are very bright, as you can see in that prior slide. They're basically as bright. If I go back, you can't really tell on this, and I'll show you an image later. These can be roughly as bright as about a billion stars for 1 month. That's the amount of energy that's being released. And so in terms of luminosities in the universe, these are the most luminous things that occur after the Big Bang, though you can't really give the Big Bang a luminosity. You know, there's no observation of the Big Bang in this sense. Okay, so as a physicist, of course, I feel obliged to teach you some physics. This is also important for those of you who do statistics, so this is an important thing. So what happens in these supernovae is very simple. In almost all cases, I have a star, that there's a source of energy at the center that's suddenly so large, everything is unbound and just moving out at some very high velocity. Typically 10,000 kilometers per second. Okay, so for the radius of the Earth, that's 2 seconds to cross the diameter, or 1 second roughly to cross the diameter of the Earth. That's how fast this material is moving. In that material, there is material, hydrogen, helium, all the elements, but the energy is not in the material. The energy is in radiation, photons. That's where the energy actually is. And those photons would like to move at the speed of light. Well, actually, not like to. They do move at the speed of light. And for me, that's not one. That has a real unit to it. And that is much faster than the material. The material's trying to only go at 10,000 kilometers per second. The speed of light is much faster. Well, the photons can't just leave because the material that they're in is causing those photons to scatter in that material. And so they can't just, as they say, free stream out. And so here they say are 3 different photons. Let's call them red, green, and blue. Why not? And they're trying to get out. And what they're doing is random walking, because every small distance, which we call lambda, the average distance they move between scattering events, in this case from electrons, is very small compared to the size of the object. And so you have to wait until they random walk us out, and that takes a certain amount of scatters, n, because on average, if I'm taking a random walk and I take 1 step to the left, 1 step to the right, 1 step, et cetera, over time then, I will not be moving in a straight line. Instead, I'm just diffusing at a much, much lower rate. And so the distance I've moved after n times of scattering, all these little scatters, is the square root of the number of steps times this typical distance. So this is the random walk. This is the same reason when you, for example, have a poll and there's 100 people that have been polled, and you say, well, what's the error on the poll? The error if you talk to 100 people, the error is roughly going to be square root of 100, which is 10, which means that you've got a 10% error if you only talk to 100 people. Now, of course, in my experience, about 10% of people are crazy, so it's sort of in the noise. But so that's why this is, okay? That's the square root of n that you should be familiar with. Okay. So what does that let us do? Well, that actually lets us calculate the rate at which those photons are going to leave. And that's, of course, the luminosity. That's what we see. We don't see the matter. We see the photons that get out and come to us. And so the time then it takes for that is the average time between scatters. This is the speed of light. This is the average distance moved. That's the diffusion time. And if I just put in that formula I just derived, that gives me r squared, the current size of the explosion, the exploding material, divided by the mean free path and the speed of light. And the mean free path just depends on how dense the material is. As it's expanding, that material is getting less and less dense, which means that on average, the photons get to move further and further between each scatter. And so eventually there comes a time where the time for the radiation to get out equals the age of the event. Is it day 10, day 100? There comes a day where suddenly the radiation can escape. And that's just this simple number. If you do the algebra of setting this equal to the age of this typical characteristic age, which depends on what we call the opacity of the material. How opaque is it? This you're familiar with, especially here in Santa Barbara, where you can really see the difference when there's fog and not fog, or haze or not haze, or if you're in LA, it's different, but we're not going to talk about it. That's the opacity of the material. This is the mass of the envelope that was ejected. This is the velocity, that 10,000 kilometers per second, and this is our friend, the speed of light. So that gives you a typical time of 10 or 20 days. That's the duration. So I've just now explained to you why they last as long as they do, roughly. Why is it not a millisecond? Why is it not a second? Why is it not an hour? It's this. It's the time it takes radiation to get out. Before the radiation gets out, it's just undergoing what's called adiabatic expansion, just as in the early universe, and the temperature of those photons is just being redshifted by 1 over the current radius of the object. Okay, so I'm going to just jump ahead and tell you, now for those of you who like equations you can follow, I can just give you the punchline. You can use this calculation to actually get the brightness of the event. And what it ends up giving you is that it depends on the energy of the explosion. That's the supernova energy of the explosion, the speed of light, the initial radius of the star, this opacity of the material, and the total mass that was in there. This is a number which ends up being independent of time. So this calculation tells you there's a plateau luminosity, constant luminosity, until that radiation starts to leak out. And if I put numbers in, I get 10 to the 9 solar luminosities for an object that exploded when it was what we call a red giant. And so I'm showing you this because it's true. This is the theorist version of what it looks like. Actually, this is a theoretical calculation of one of these explosions called a core collapse type 2P. And just it's just how we understand the duration. Again, to me, 20 days is the same as 50 days. Sorry, Wayne, you're right, or whoever mentioned pies. Okay, to me, 20 is the same as 50. But yes, if you're building a telescope, there's a difference. I understand. Prices go as a high power of these errors. Okay, so that's how we understand that. And what's made from these and that we observe are these remnants, neutron stars, that are sitting here in the center of all this material that's been ejected. This is the Crab Nebula from a supernova that happened in 1054 AD. So it's roughly 1,000 years old. This is all the material that's been ejected. And here's an object with the radius of 10 kilometers, roughly the mass of the sun, spinning at 33 milliseconds. So a day on the neutron star is 33 milliseconds. Okay? Lower mass stars actually don't have nearly as dramatic of an end to their life. Less massive stars just sort of peter out, only getting to carbon and oxygen. They never get hot enough to actually do further fusion. They form what we call a white dwarf, an object with the radius of the Earth, not 10 kilometers, but 6,000 kilometers. Cool with time, but they do eject material, and this is material that's been ejected from this object. Then the bright, intense ultraviolet light from this young white dwarf is causing fluorescence in this exiting material. And these are called planetary nebula, though there's nothing to do with planets. Okay? So this is one thing astronomers love to do, which is misname things to confuse the audience, or more importantly, to confuse the physicists. Okay? Okay, now I showed you, anybody know what these, this image is? Yeah. Wayne, you're not allowed to answer. We have Pleiades, yeah. Wayne? Pleiades, okay. Stu looks like he knows. No? No, you're not going to answer. Pleiades. This is the Pleiades constellation. These three stars, three of the brightest stars, are binaries. Two stars orbiting each other. Most people don't appreciate that because, of course, our star doesn't really have it. Well, we're not in a binary, except we're orbiting it. Jupiter's orbiting it. But half of the stars on the sky, roughly, have a star comparable to themselves in an orbit in a binary, what we call a binary. So these are double stars where they're physically actually orbiting each other. So that's a very common occurrence, and that's stars, as they form, typically half of them do that. And that allows for another way for stars to die, which is you take one of those white dwarfs that you thought was done, and this is the artwork done by Tony Pyro, who's a graduate student here. We used it on the brochure. Take one of these white dwarfs, put it in a binary, and you add matter onto it. So just when it thought it was never going to burn again, you actually dump material onto it, reheat it, and get this material to ignite. And that happens. That happens about as frequently in the universe as these other explosions. You basically get a runaway of carbon fusion that suddenly, in 10 seconds, literally, burns most of that material to nickel-56. Nickel-56 is a radioactive element, and I'll explain in a minute why that's important. But it decays in the end to iron, and roughly 2/3 of the iron in your body was made in the explosions of these objects triggered in this thermonuclear event. That's roughly 2/3 of the iron is made this way. They look like this. Again, you just find the arrow, and there it is. You can already tell from this image they're a little bit brighter, and they are. On this plot, let me just go to here. They're typically about a factor of 10 brighter. Again, here's all the stars in the Milky Way, and these are another type of supernovae that we call thermonuclear. And we have to understand them in the same way. I don't have a choice. I can't build a new sort of rough picture, but I do have a puzzle, which you can already tell from here. I gave you a very nice derivation of this luminosity. You might not have understood it, but trust me, I didn't cheat. And suddenly I'm up a factor of 10. Well, that's, a factor of 10 is meaningful for astronomy. That's why we use the log scale. Okay? Okay, so a factor of 10 is, that's not the same number. A factor of 3, between friends is okay, but 10 is a big problem. So how do we understand this brightness? Well, what we realized, the community realized, this has been known for about 30 years, is that nickel that's made is radioactive, decays to cobalt, decays to iron. That peak in the light curve and the duration is still roughly, because it's roughly a solar mass of material. However, the radioactive decays of these elements are actually what's providing the luminosity at the peak. So this thing is a solar mass of radioactivity, and that's what sets this peak brightness, is the radioactive decays of those elements. Okay? And by coincidence, it's only a factor of 10 brighter. It didn't have to be, right? The radioactive decay lives could have been shorter, could have been longer, but that's where we are. Okay. So those were the two events, broadly speaking, that we knew of, that we've known about for a long time. And what I want to start transitioning into is how our eyes have been opened to other types of explosions and how those are providing sort of theoretical challenges to the theory community. And I'm going to talk about how that's happened. So I would say the big revolution that's occurred for this type of science is the ability to survey the sky and do difference imaging of what's different from one night to the next. If I could take an image tonight, take an image tomorrow night, and literally just subtract one from the other, I'll find out what's different. And that requires a large amount of imaging area, which CCDs, as their costs have come down, have made possible. That requires the ability to do the computations to manage the large amounts of data. Those two things in concert, and transport the data, for example, off the mountain to a place where you can compute, has allowed for a plethora of supernova surveys where basically what I said is what they're doing, taking images night to night. And the survey I've been involved in is called the Palomar Transient Factory, and I'm going to highlight one result from this as I go on, but it's an important example of what's happening in the field. So you heard about the effort at Las Cumbres Observatory to build networks of telescopes that will do continuous coverage. The question is, who's going to tell them where to look, where things have changed? The way you do that is by these surveys. And the Palomar Transient Factory has taken the 48-inch Schmidt telescope at Palomar, which did the Palomar sky surveys. So for those of you, the glass plates from the Palomar sky survey are about yay big. They were literally photographic plates. So what's happening in this project is a CCD camera has been purchased, which is about that size, about 1/7 of the area. Okay, Wayne's correct about that big. Because, eventually we'll be able to afford a full one, and we'll see. And you basically just do the Palomar sky survey every week. Why not? Right? It doesn't take you 10 years. So roughly, you're scanning 10% of the sky every week. This is finding hundreds of transients per year. And what I'm going to talk about in the last part of this talk are two types of events that are one of which was already found prior, and then another type of event that's very faint. So I'm going to talk about the extremes. My prime scientific interest in these collaborations and others is basically in understanding the weird events. The unweird events, I would claim we understand them. Yes, might have other purposes, but as they always say, don't ask what the stars. Let's see, I can get the sign wrong. Are you working for the stars or are they working for you? Okay, I'm working for the stars. Right? I don't want to use the stars to do something else. I want to understand the stars. Okay, now this is a slight philosophical comment. So I want to remind everybody of the importance of observation in the field of astrophysics. We're still in a century, hopefully, of discovery. And therefore, it's very important. I've sort of dragged you through some of the observations, but I'm sparing you a lot of the details. But in the wonderful book written in 1958 by Martin Schwarzschild, who was a professor at Princeton, called Structure and Evolution of the Stars, he has this wonderful paragraph, which I give to all my graduate students when I first teach a class. So this should be read out loud, so I'm going to. If simple, perfect laws uniquely rule the universe, should not pure thought be capable of uncovering this perfect set of laws without having to lean on the crutches of tediously assembled observations? Notice crutches. True, the laws to discover may be perfect, but the human brain is not. I will second this motion. Left on its own, it is prone to stray, as many past examples sadly prove. In fact, we have missed few chances to err until new data, freshly gleaned from nature, set us right again for the next steps. Thus, pillars, rather than crutches, are the observations on which we base our theories. Now, I put this up outside my office about 6 or 7 years ago. And it was very interesting to see which of my colleagues wanted to come and have a chat with me and ask if I was sending a message. David understands. So it's important to understand, and of course, as a theorist, I want to be ahead. I don't have full confidence in Schwarzschild's statement. I'm not going to stray. We're going to get the right answer, right? But the beauty is we're going to find out whether we're right or wrong. Okay, so I first want to tell briefly the story of the very bright events. They were first found with this dinky little 18-inch telescope, out of which is not really a great image. That was the Texas supernova survey done with this telescope by Robert Quimby and company about 3 or 4 years ago. These are what the data look like, which are not pretty for you. This is magnitude on the sky. Your eye, unaided, can see a star with roughly magnitude 6 let's say, if you're lucky. This is magnitude 18. 5 magnitudes is a factor of 100 in brightness. Okay, so that gives you a sense of how much fainter these are, but this is a little dinky telescope. What he found were these very bright events. You can't see from that how bright they are. This is the tediously assembled observations, which we will call pillars for today. These are showing, of course, once there's one, there's many. Once somebody recognizes a new phenomena, others realize they had the same thing, but maybe they got scooped. This is what's fun about the field. So here's your typical type 1a. The thermonuclear event I showed you is this. This is time on this axis. Days since the maximum of light. You don't really know when the explosion happened. You just know that you saw maximum light. And then this is this magnitude scale, where this is a factor of 100 in brightness. So here are the objects I talked about, the typical core collapse events. These flat lines are here. Here's a typical supernovae. These events that we're seeing, and now there's many of them. There's now 15-ish, I want to say. Andy, 15, 20? Are, as you can see, about a factor of 30 to 50 brighter than these thermonuclear events. And they last a very long time. So the radiated energy is huge. Right? We're up a factor of, from this event, up a factor of 100 in brightness, and even in duration, they last a long time. So these are very energetic explosions that were not predicted, pretty much not predicted by any theory. So who ordered this? So here it is on my scale to keep track. Here's what these events look like. Here's the thermonuclear events. Here's the core collapse. Well, what do we know? And this is more or less getting a little bit tuned up. We know that they're associated with actively star-forming galaxies. They're very likely massive stars. By massive, I mean 10 times the mass of the sun. As you can see, they're nearly a factor of 100 times brighter. Because of that, of course, you can see them at much larger distances. And so you can get a rough rate, which is, these are rare, about a part in 10 to the 4 of these events. So they're not common at all. You might ask, why did the observer with the dinky little telescope find these? He's competing with people with 2 and 3 meter telescopes, covering volumes of the universe a factor of 100 times larger. Anybody want to guess?
Right?
No. He wasn't distracted by all those boring events. That's my theory. The people who do the supernova surveys are finding 10 a day. They're so busy tracking down the regular things, the oddities get put aside. I'll think about it on the weekend, maybe next week. But I don't know, I'm looking to Andy if he can correct me, but it's still a puzzle, actually, because there's no reason, and actually all the other surveys now have them, or know they have them, but you know, they were scooped by this. So it's a fun field in that sense as well for the sociology. Okay, so I'm going to briefly tell you about a theory very quickly as to how we tried to understand these. So I showed you the algebra that gave me this luminosity. And of course, if I want to fix that algebra to go up by a factor of 100, I don't have a lot of options. So if I go back to my formula that we're going to trust for a moment, and you can say, well, can't you just fix it? Here's my formula that gave me the brightness. The energy of the explosion, I'll tell you, I don't have a lot of freedom there, not a factor of 100. That's the speed of light, right? And in this talk, I'm not allowed to change the speed of light. This is the radius of the star. Well, I can't change the radius of known stars by a factor of 100. That's just not an option. This is the opacity of material. This is, for the physicists in the audience, this is electron scattering. I can't change electron scattering. This is the mass of the star. I can't reduce it by a factor of 100 to crank this up. So I've got a problem. Okay. So where there's a will, there's a way. And so what Dan Kaysen and I did a year ago was this realization that about 10% of the time when you have these core collapses, you make it an unusual, this is, again, a very expensive NASA image by an artist, of what's called a magnetar, which is a neutron star with a very high field. This isn't going to mean anything to you, probably. The Earth's field's, I'll see how I used to know in a Tesla. Anybody remember in Gauss? It's a half a Gauss, yeah? Okay. So this is 10 to the 14 times the Earth's magnetic field, but that, that number doesn't mean anything, probably. These are neutron stars that are born with this is called very high magnetic field. And what we realize is that high magnetic field allows you to tap into another energy source, which is the rotation of the object. So the energy sources we've talked about so far are nuclear energy, gravity, things falling in, and now I want to use rotation. If I want to use that rotational energy, I need to get it out fast. And what this magnetic field lets me do is get that energy out fast by basically, if I take an object that's spinning with a strong magnetic field, it radiates electromagnetic radiation that takes out the energy from the spin and puts it into electromagnetic waves. And at this field strength, I can do it in time. I need to do it pretty quickly. And so I'm just going to tell you, if I have one of these that's born rapidly spinning 2 to 20 milliseconds, I can actually get that rotational, I can tap that rotational energy source on the time scale I need, which is the time scale of that event. And you can spin a neutron star up to about 1 millisecond before the centrifugal forces rip it apart. So I'm extreme, but I'm not too extreme. Again, for the algebra, for those in the crowd who want to track, how in the hell did you do that? You can take this formula. We did more than this little magic trick. You basically reset the energy scale by using the rotational energy instead of the supernovae energy. That might be comparable. But basically, you do it at such a late time that you reset the radius scale to the radius of the envelope at that moment. And that's where we get this factor of 100. And you can naturally get these luminosities. It's a fun physics problem. So this just shows that you send out an explosion within an explosion. I have an explosion, and then I have another one, which is a rotational energy release. That pushes a bubble out. This is showing the density as a function of coordinate going out into the supernovae. This is the bubble for different amounts of energy I've released. And these are the temperatures. The money plot is the luminosity, so I'll just skip to that. These are actually computations, both analytically and numerical, just showing that I can get luminosities I need. This is the luminosity I get with the initial spin of 5 milliseconds for magnetic fields that are, as I said, a few by 10 to the 14 Gauss. So this is not so bad. Now, I've added free parameters. So for those of you who are purists, you might say, well, look, Lars, you've now added the spin, you've now added the magnetic field, you can fit anything. Well, not quite, but we do fit some things pretty well. And that's when we decided to write the paper. These were data from 2 different supernovae. This one is causing us trouble because there's another explanation. So we have combat on that. But for this event, there was no explanation. And this is a model that Dan Case and I made actually about a year ago now. And there's now about 10 of these events. And I can tell you that for ones like this, we can get more or less equally good fits. Though I didn't show it because Kate, my 10-year-old, didn't approve of it. We have another object with much richer data sets where we tried to pull a model off the shelf and see how good it looked. And I showed it to her. She said, Dad, the points supposed to go through, or the lines supposed to go through the points? I said, yes. She says, that's not so good. So she doesn't understand the impact of the log scale yet. Okay. So this was a case where the observers were first, theory followed. We'll see if this is the correct interpretation. We don't know. And there's still lots of discoveries to be made observationally. The last brief story I want to tell you about is a case where I'm going to show the same image again, but I'm just going to change the labels for those of you who are keeping track. A case where theoretical predictions were made, and events are now occurring that look like what we predicted. I'm reluctant to say it's what we said it was, because we're still struggling. I can have cases where I have a white dwarf that's dumping pure helium onto one of these carbon-oxygen white dwarfs. So this is a helium star that's donating pure helium that had burned out its hydrogen, and there's helium that gets piled up on this object. And 3 years ago, we decided to basically ask ourselves, what would happen if that helium layer that I've added suddenly did nuclear energy release itself? So it's the same energy source I've talked about, which is a nuclear energy, but I'm going to do it with a much smaller amount of mass, only maybe a tenth the mass of the sun. Instead of the full mass of the sun, I'm just going to dump on a layer and have it explode and see what happens. And so what's shown here is just an example calculation where I've put on 2/10 of the mass of the sun of helium here on a white dwarf, which is carbon and oxygen inside of this coordinate. And then I do what we call a detonation. Most of you are not familiar with detonations, and that's probably for the better. These are explosions caused by shocks that are moving supersonically. And you can see that shock wave moving out in the helium this way, and another shock wave moving in to the carbon-oxygen. The temperatures in the helium get so high that it undergoes fusion, and this is showing what's made, the elements that are made as you go out. And what you see is here's nickel-56, the isotope we know and love that I talked about. But what we realize is you also make other unusual radioactive isotopes. Iron-52 you've never heard of, I can almost promise it. Chromium-48, titanium-44. But you also have a lot of helium that's left. This is at the surface of the star. But this amount of energy release, so suddenly, you can't see it here, but this is about 1 second. So again, it's moving at about 10,000 kilometers per second. This amount of energy release in this material has it unbind. So it leaves at 10,000 kilometers per second. Well, you can now predict. It's a tenth the mass of the sun, not a solar mass. So will it be shorter or longer duration? Shorter. Okay, what's going to be the energy source? Well, the object's really small, so that R naught in that formula is not going to be so good, right? So I'm going to have to use the radioactivities, right? And indeed, it's shorter. It's going to be a 3 or 5 day event. I'm going to power it with these unusual radioactivities, chromium, iron, nickel. And on the big scale, here's what it looks like. So it's a dinky little thing, and you could say, some people care about whether it's bright or faint or extreme or short or fast. I just say it's a phenomenon that's not been observed. So in 2007, we were very bold, and we made this prediction, that you should see these. And the anecdote is that many astronomers, I'll leave them unnamed since this will be broadcast, said to me, Lars, I've never seen that. What you're saying can't be true. And my answer was, you're not looking hard enough. Because, you got to challenge them. I mean, we might be wrong, but it's fun it's even more fun when you're right. When we did this, we realized they were a tenth as bright for a tenth the time. And so a friend of mine, Chris Stubbs, many of you know him, he used to be on the faculty here, said, well, if they're a tenth as bright for a tenth of time as a 1A, you should call them 0.1As. So that's what we called them. That name has stuck, though I was recently informed the error in this name, and Wayne, I'm looking to you to fix this for me, is that it's hard to Google. 0.1 it's a hard thing to do. So this is an error we made. We never thought we had to filter our names so that Google would function. So there you go. All right. So in fall 2009, I got a phone call from Dovie Poznansky, a postdoc, who was looking through some of the old data sets and said, I want to give a talk at the meeting at KITP in the fall. I can't tell you why, but you're really going to like the story I'm going to tell. And I said, well, I'm not sure I can do that. I mean, I'm running this conference. He said, no, trust me. And I said, okay, but, if this is bad, man, you only get one chance, right? And what he found was a very rapidly decaying event. So again, this is magnitude scale. So this is 5 magnitudes is a factor of 100. So this event fell in brightness a factor of 115 days. And here are other events showing you how much slower they go. So this was the first candidate discovered in 2002. By the telescope, discovered by human beings in fall 2009. Okay? Well, there's one where there's many. And Palomar Transient Factory has a fantastic candidate, we think much better. That's the clumsy name, 10 BHP. It was also found by the rest of the community, so it has a more traditional astronomical number, 2010X. I'll show you, how, again, decays in 5 days, velocities of 10,000 kilometers per second. It shows calcium, carbon, titanium, iron, the things we predicted. We'll see. We had models, as they say, on the shelf that you can plot versus the observation. So these are the data. These are 2 of our models that were sitting on the shelf, not postdictions, but predictions, of roughly a tenth of a solar mass of material, and the rest being nickel. So we'll see. It's exciting times, and again, because of everything that's happening, our expectation is there will be more of these. This is not a dying field. This is a growing field. And for something like the Las Cumbres Observatory, this is an example where rapid response and the ability to follow something is good because these things are short. So we'll see. So the big question is, now I've expanded my scale. As you can see, I was only showing you these 2 before. These are the really bright guys. These are the faint guys. And of course, the big question for the observational community is what's next? What are the observers going to find? And in this time of surveys, we'll see if they can get anything up here. At some point, I'm worried about, E equals mc squared on your tie gets to be an issue, for some of these energies. Okay, so that's for the observations, and then of course on the theoretical side, one project that people don't know about that I've been very involved in just today had the paper accepted. So Bill Paxton and I and Aaron Dotter, Falk Herwig, Pierre Lessoff, and Frank Timmies have been working for about, I'm looking at Bill, 6-7 years on building a new tool, computational tool, for basically doing stellar astrophysics called MESA. And this paper was just accepted today, actually. It's quite good timing. It's rare the journals cooperate with real time. And of course, we have a logo, right, Bill? And a hat. Thank you very much.
Thank you, Lars, for an explosive talk. We always have questions and answers in our public lectures. As you all know, many of you attend them regularly. And Lars would be delighted to answer a few questions if there are any burning questions. Derek, let me give you the microphone.
First of all, Lars, congratulations, and everybody, and that was a fabulous talk. What releases the rotational energy that ends up causing the release of light? Is it the explosion which terminates the rotation, or what?
For the case we showed and we talked about, it's the fact that what's born after the explosion is a neutron star spinning at, let's say, 10 milliseconds. That sounds fast, but for a neutron star, that's not that fast. And because it's highly magnetized, the spinning and the magnetic field's misaligned. That rotation of the magnetic field creates electromagnetic waves that takes the rotational energy and turns it into what we call Poynting flux in the physics world, though that itself is a big problem as to how that actually works. But we observe spin down of neutron stars like that and less magnetized at the rate expected from just a rotating magnetic dipole. So you need the magnetic field to have that happen.
I find it more interesting that
Hang on a second, sorry. We want to get the...
That you have a spherical collapse.
Yeah.
Why would you get an oriented magnetic field?
Okay, so the dark secret in astrophysics, right, is we do everything presuming spherical symmetry until we're absolutely forced to relax that assumption. And so you're absolutely correct. If everything was spherical, you couldn't get those end states. So we know stars rotate. We know stars have magnetic fields in them when they're made. We don't understand well what sets the magnetic field strength of a star when it's born, or when in this case, the remnants of stars. And so there's stories that we tell about how those magnetic fields get made, primarily due to convection and roiling motion, which, if you have rotation and convection, ends up not being symmetric at all, but you really start to break symmetry. So it's still a fundamental question as to what sets those magnetic field strengths. And the short answer is we don't. We have stories, but I would say it's not pretty. We observe them, so I'm just sort of using it at this point.
I think everybody might be exhausted and on the point of collapse, so let's all explode into the courtyard for refreshments.